Hello and welcome to C++ Weekly. I am your host, Jason Turner. In the episode, I want to discuss stack versus heap. This is an episode that was requested by someone. So let's go ahead and talk about the difference between these things. The most important thing to point out is that the C++ standard really doesn't talk about this topic at all. But we can kind of reason about it from the perspective of what operating systems and computers do. This episode is sponsored by JetBrains, and I wanted to let you know that I do personally use CLion in my work. I find the refactoring tools to be particularly valuable. The safe delete feature has saved me a ton of time when I've been doing refactoring on large projects. I can get analysis of my compile time checks and see when something is wrong or fails to compile right here in my IDE. So be sure to check out the links in the video description for a discount code and more information about how you can check out CLion. As a general rule of thumb, automatic variables, these things that are lexically scoped, things that are scoped within braces, are stack variables, and dynamic variables, things that are created using new and delete, are variables that are heap variables. What we can observe is that as the stack objects increase, the address decreases. It goes from FC to F8 to F4. And as the heap objects increase, as each new heap object is allocated, the address increases starting at a low value. This is, again, not required by any means, but this is what we tend to have. As we've got some address up here, and going down is the heap. And we've got some bit of unused memory. And this is where we have the stack. So they're just eventually going to meet, and that's a problem. That's a stack overflow. Although practically speaking, on our 64-bit addressing, they're never going to meet. But we do have the practical problem that stack space is considered to be limited. It's limited in some way that is defined by your compiler, by your operating system, by your machine in some way. And the heap space is kind of unlimited, maybe on modern architectures. It's limited by how much virtual memory your computer can address. I wrote this out as if this is a 16-bit address space. That would be more accurate for 64-bit address space. Not that that really matters here. And as we can see, it's not even actually using the top bits of this address. It's some other thing, and it changes every time the program runs because there's going to be some sort of randomization going on in here. The heap we can generally reason about. This is going to be slow. Pointer indirections. Cache misses. These are things that we think about when we think about variables that are on the heap. When we think about variables that are on the stack, these things are fast, known locations, that kind of thing. So if I were to illustrate with Compiler Explorer here, I'm going to forward declare some function. It's going to take an integer by reference because that is the simple thing to do. As soon as I do this, I can no longer execute the program because I'm going to have a forward declared function that I am not actually able to call because I never implemented it. But let's go ahead and take this int I here, and I'm going to call useInt with the variable I. And we're going to go back over here and actually look at the Compiler Explorer output. This will generate a lot of output because we're using println and we don't have optimizations enabled. But let's go ahead and do this reveal linked code thing here. Now I see that I've got this useInt, and it's setting up this parameter. I'm going to go ahead and turn on some optimization so that we can see a little bit better what it does. But the compiler is basically able to say that from some sort of current known base pointer or stack pointer address minus some fixed constant, that is the address of the thing that I want to use. So I'm going to go ahead and pass the address of that thing to the function being called. So let's go ahead and hit this reveal linked code again. We can see here that the, compiler says current stack pointer plus 12 is going to be passed to the RDI register, and then I'm going to call useInt with that thing. And if I turn on more optimizations, it's going to simplify this code even more. But it does know exactly where this value is effectively. So let's create a different variable. We can see again that to call the one that takes a reference, it's going to take current stack pointer plus 4, basically. RDI is going to be the first parameter to this function, useInt. But then when it wants to call the one that has a heap allocated object, it has to call operator new, and then it has to get the address of that thing, then copy that address into RDI, and then pass that address via RDI into useInt. So it doesn't know where the thing lives. This is why we're going to say that stack variables are faster. It is a add. It's a very simple, fast add to know the address of the stack variable. And often stack variables can be entirely eliminated. That is at a very high level the difference between stack versus heap. Hopefully that made some sense, and this gives you some idea for why you should prefer stack-based variables. Let's go ahead and try to overflow the stack though real quick so we can actually see what happens. I'm going to turn optimizations off, and we're not going to actually call any of these print address functions. We're going to drastically simplify all of this code, and what we're going to do is just create a local array of integers. Now, if I create 1k of integers, is that going to be enough to cause this program to fail? Oh, well, I have an error on an unused variable. Well, yes. I intentionally turned optimizations off, because if I turn optimizations on, then the compiler is just going to go ahead and completely get rid of all of this entirely, and it becomes an irrelevant exercise. So what does it do? It sets up some stack space right here, 3976. All right, it doesn't seem to have a problem with that. What if we set up 1 million of these things? Nope, still not a problem. This is executing just fine. What about a gigabyte's worth? No, I'm getting a weird stack pointer thing here. It doesn't seem to actually be doing anything. It's just doing the register calculations. So we're never going to get the stack overflow. We need to initialize this with something. There we go. Program terminated with segv. And that's not a problem. So there is a limit. How much stack space is there? Again, like I said, it is limited by your operating system, by your configuration, by your compiler, by your optimization levels. There's all kinds of reasons that this thing might be limited, and we can kind of narrow down exactly how much space it has. Okay, again, I hope this episode was interesting and informative. Investigate this on your own. I'm sure I left out things that someone watching this thought was important, so go investigate and leave comments. And thank you for watching this episode of C++ Weekly.